First, let me say that this presentation will be on the GAR's website when David gets it there. So there's a lot here, and the limited time I've got, I'm going to go pretty fast over the systems that are decommissioned, and we'll spend more time on the active systems. Question why, what's the interest to hams? Well, for one thing, we actually share some frequencies with the navigational systems. And in those frequencies, we're secondary, and they're primary. And currently, there's only one that I'll cover that is currently active. The other systems have been turned off or decommissioned. Anyway, I'll go through that. And I like to limit questions to maybe one per slide because at the end, you can all the questions you want, but due to the large amount of data. Anyway, I'll start off with the types of radio navigation systems. And we have what they call hyperbolic navigation. And that gives you a precision fix. Your GPS works on that. You get two stations, you get the high part, and I'll show you a drawing. Hyperbolic lines between them. And that'll give you somewhere on that line. Then you've got to have a third station to get another line to get a fix, which I'll show that. We have systems that give you direction only. In other words, direction to that point. We have a nav aid that gives you slant distance from, say, an aircraft to a point. And that is slant, so if you're flying right over top of it, it's going to still say you're a mile up or a mile away or whatever. We also have what the instrument landing systems. And it tells the aircraft where they are on their approach. I have aircraft that transmit data to the ground, and that's sent to the controllers and also the airline companies if it's a commercial aircraft. And we have what the old radar, which is the aircraft position, and it can give elevation, speed for the FAA controller. And we go to the first, see what it does here. I'm assuming that this is looking the same. All right, these are the systems I'm going to cover, and they're listed in frequency order. It starts out 10 kilohertz, and the last one goes up to 9.5 gigahertz. So those are the systems. You may say, well, how about so-and-so? Well, I didn't know about that system. So that's the reason if I'm leaving one out, it's because I didn't know about it. And if you notice what type it is, the frequency range, and over here are the dates. In this case, it shows that it was discontinued in 1997. You see if I can make this smaller. Okay. And so let's start out with the Omega system. I'm using the internet. I've got it locally, but I'm using the internet, so that's why it's slow sometimes. Anyway, it provided worldwide navigation and use phase difference to determine location. Those are the frequencies, 10, 13, and 11 kilohertz. There were 8 stations in the chain, and each transmitted about a 1 second pulse. These are where they were located. I won't go through that. I'll show you a chart. And the accuracy was 3.1 to 6.2 nautical miles any time of day. And the output power was 10 kilowatts. All these have references. Now, this actually takes you to a Wikipedia page. So all the information you ever want to know is on each one of these. This is the chart. You see, I may have to switch back to my local. Okay, there's the, shows you where the stations were, for whatever that's worth. So, let's see, back up. All right, let's go to the next system, which is DECA. And basically is land-based navigational system where we change, I should say. Each station transmitted to its carrier. You had a master on 85 kilohertz. You had slave stations on 70, 113, and 127 kilohertz. And they were labeled blue, green, and red. And the location was determined by the phase difference in the signals. Daytime range was 400 nautical miles, nighttime was 200. Accuracy at daylight was 50 yards, and nighttime was 200 yards. And it's 60 to 120 nautical miles between the stations. So, yeah, I'm going over these fast because they are decommissioned. Iran C, which was decommissioned in 2010. It operated on 100 kilohertz and uses pulse modulation. The location was based on the time between signals, again using hyperbolic curves. The stations were arranged in chains, and you had 2 to 4 slaves, master and 2 to 4 slaves. And the master sends 9 pulses, where the slave only sends 8. And each chain was determined by the group interval rate. And on your equipment, you would set that up to read the change. Output power was 100 kilowatts to 4 megawatts. Range was 800 to 120 nautical miles, and the accuracy was 150 to 600 feet. And repeatable accuracy was 50 to 330 feet. In other words, if you came back tomorrow and get your fix, you would be within that range. And this is, now, you used to have to use a chart. Let's see if I can blow this one up. Okay. All right, I don't know if you can see these little lines. There's some green lines there, and I don't know what color those might be. Can those show up at all? They're not very, but that's what your charts had on them. And when you looked at your instruments, it would give you a time difference between the stations. So you go right here and say, okay, that's my time difference. Well, I'm somewhere on that line. I don't know where. Then you go to the second station, and you get another, and that's what these lines are for. And where the lines cross is what you're fixed. In the late 90s, the computers came along, and so just read out your latitude and longitude. You didn't need charts anymore. So that's gives you an idea of how hyperbolic navigation works. I think I'm going to switch back over to, I'm trying to use the internet, and evidently it's not.
You're in a pop-up window, just close that or minimize that.
Yeah, let me know, because I don't see it here. So let me know what's wrong.
Yeah, so you just haven't minimized that.
Okay, let's see. Right there.
Yep.
There we are. Okay. Back to, okay, this is NDBs. This is the first system that I'm going over that is actually in use today. And I'll spend a lot more time on it because a lot of the, I don't know why that is in the middle. So we were there, let's go to this, and we were getting ready to, all right, NDBs are non-directional beacons. They first came out in 1928, and they're still active today. They operate in North America on a frequency of 192 to 435 kilohertz, and also from 510 to 535 kilohertz. And the classes and ranges, they have a compass locator, which can be received up to 15 nautical miles. They have an MH, and I'm assuming that means medium high, because I did not find what MH means. But that's in the charts, it's listed like that. 25 miles, H is 50 miles, and HH is 75 miles. And the power is from 15 to 2,000 watts, depends on the station. Transmits a continuous carrier, and it's modulated with a 2 or 3 character CWID. And we have a compass locator, which I'll explain in the difference in a few minutes. We have a compass locator here at this airport, Briscoe Field, and it's located about 5 miles east of the runway. And this is, if you tune the frequency, it's 419 kilohertz, and this is what it sounds like. Don't hear that? So if the pilot was listening, he has that tuned in, he would hear that. And if he can't copy code, it's actually on the charts, it shows dots and dashes, so he could figure it out that way. All right, we have another one, and this is a Flowery Branch at the Gainesville Airport, and it's on 365 kilohertz. And it's not a compass locator. I mean, again, compass locators only have 2-character ID, and it's and let's see, listen to this one. And again, that was copied at my house. So if you have an HF receiver that goes down below AM broadcast, you can pick these up. And at nighttime, you can pick them up all over the country. Of course, you need to be able to copy code because they're all Morse code. I'll write down the info. Sometimes weather and other information is provided by voice. The received equipment is 2 loops that are 90 degrees apart and a sense antenna. You have an ADF indicator in the aircraft, and it's slowly being decommissioned. The sites that the FAA runs, they're closing them in favor of GPS. Again, here's the references. And this is actually a picture of an instrument in an aircraft. It shows the direction that the aircraft is flying, and the arrow points to the NDB. Okay. This is the pattern of the antenna. You have the 2 loops, you have the sense antenna, and you combine all of them together. The composite signal is this signal, so you can get a direction. Normally loops, bi-directional. That's how you get the one direction antenna. Here at this airport, here's a Google Earth picture of the one that's located, again, it's about 5 miles from here. And I've got better pictures of the different NDBs, not this one. But this is a pole here, and there's wires running between the poles. And this is the feed going up. And this is the transmitter shack. What you see here is the 75 meg antennas, marker antennas, which I'll cover later. Anyway, that's the picture of the one here. This is a better picture. I don't remember where I got. All of these came from Google Earth Street View. So this one you can actually see the antenna. I don't know if you can see the wires, but they come up here. That's an insulator. There's 3 wires between the poles. They're shorted at the end. And actually, that's a top hat because it is vertically polarized. So your vertical is right here. The rest of it is just the top hat for loading. Let's see, I've got some more pictures. This is a little different design. You have a tower, you've got 2 wires. They're not shorted at the end, but they are shorted in the center. And I'll have a picture of that on one of those in operation. And let's see, the Flowery Branch NDB, you can't tell much about it because, again, this is Street View on Google Earth. There's one of the poles are here, transmitter is here in the center, and over here is the other pole. And you can't see the wires because you've got electric lines from the highway. So, sorry about that, but that's the one that, for Flowery Branch. Let's see. Here's an interesting one. This is a vertical with a capacitive top hat on it. And this is actually located in Lithia Springs, and it's the compass locator for the Fulton County Airport. And I'll show you a chart in a minute. And if you notice over here, there's also a Yagi that looks like it's pointed straight up. And that's a marker beacon we'll cover. Let's see. Okay, next. Where was that's there. Okay, here on a chart, on a aeronautical chart, the one we just showed you by the lake there, and it shows you the symbol here, these little dots, and shows it right by the lake. This is its name, they call it, and the frequency, and the call sign it sends, and then the Morse code. And this is the Fulton County Airport. So that lines you up with runway 8. Here, there is a approach chart for this airport. This airport FAA identifier is LZU, Lima Z uniform, LZU. And it shows here the location of that compass locator. They also call it a location outer marker, which we'll talk about. Frequency again, and then we'll cover these other symbols as soon as we get to that system. Let's see. Here's the one for Gainesville, and it shows it right here. Flowery Branch, frequency, and the BCWID. The airport's here, and it's right in the landing pad. This is an interesting one. This one is 2 kilowatts, and it's in Dixon, North Carolina. And you don't have any problem hearing it here if the receiver will go down to 198 kilohertz. That's the antenna. It's a full vertical antenna. I'm showing you there. And then you may say, well, what's this antenna? Well, this is a distance measuring equipment, DME, which we cover later. It's up in UHF frequencies. But they have one there. But that's a picture of the 2 kilowatt station in Dixon, North Carolina. Here is another one. I'm not sure where I found this one. It shows the birds on the top hat, the vertical. And then this is the marker antenna, which is pointed straight up. 75 megs, which we'll cover in a few minutes. Anyway, again, all these are from Google Earth or Street View. And if I have time at the end, I'll talk about Street View. It's some interesting things you may not know about it. Let's see what. Okay, this is the one using the steel towers that we showed you the. It's got two antennas, and the feed line is in the center, and that one is in Thomaston, Golf Tango Papa. That's the Thomaston, Georgia. There is a whole website dedicated to NDVs as a hobby of picking them up and logging. And again, at nighttime in the winter, and you can hear all over the country. And it's best to have a directional antenna, a loop antenna, because a lot of them are on the same frequency, and you hear both call signs mixed together. And since they're not synchronized, they'll slowly drift, and you actually be able to hear between and pick the two out. If you're interested in it, there's the website for that. Any questions on NDVs? Okay, we'll move on to the next frequency. And that's going to be DGPS, deferential GPS. And it's currently operated by the Coast Guard. The purpose of it is to make the GPS measurements more accurate. They actually have a sense antenna at their site that receives GPS. They know where their site is, they calculate the difference, and they transmit that as data. It's transmitted on 28 to 32 kilohertz. And this will only be decommissioned also. There are PCs, I know there are apps that you can download, and you just feed the receiver into the sound card, and it'll actually decode the info, if you're interested. This is a reference antenna, GPS reference. It receives the GPS. This is one of the sites, and it's a full 408 antenna. And this one is located Driver, Virginia. And I have another one here that's in Bobo, Mississippi. Looks the same. It's somewhere between, chart. It's somewhere between 283 and 325. You can go on the Coast Guard site. We have a whole list of them that tell you the status and what frequency they're on. Let's see. Okay, let's move right on up. The next system is Loran A, and it was operational from 42 to 85, and it measured in a hyperbolic system. Now what's of interest here, it operated in the 160-meter ham band, and I can remember hearing it. So it operated on 1750, 1850, 1900, and 1950 kilohertz. These last three being in the 160-meter band. Day range was 500 to 700 nautical miles, and night was a lot further, 1200 to 1400. Again, it's not operational anymore. Okay, marker beacons, which I mentioned a little bit about a while ago. They operate on 75 megahertz. Antenna pattern is straight up. It's used as part of the instrument landing system at the airports. You have three types. You have an outer marker, mark OM, you have a middle marker, and you have an inner marker. Now, here at this airport, they have an outer marker, and which I'll show you the chart again. And as the aircraft flies over it, you will hear a 400 hertz tone with dashes, and it illuminates a purple lamp in the aircraft. It's normally located 4 to 7 miles from the runway. And this is what it sounds like. You hear that at all?
Can you do it again?
Yeah, you do it again. That's all it does, okay. Go to the middle marker, and I don't know how many of those are still around, but if you have a fly over an airport that has it, this is what it sounds like. For that. And inner marker, there used to be one at Atlanta, on runway 9 right, because I remember driving out of the airport, and I had my receiver tuned to those frequencies, and you can actually hear it. And it sounds like this. The purpose of it is to tell the pilot where he is along the landing runway. Here's some, I'll go back and show you. This is the airport here, and this is the symbol for the outer marker, right here. And let's see, another one. This is the ambulance information manual, and it shows where they're located. Like this is the outer marker, it tells you about the light, and the middle marker. And they don't show an inner marker, so I don't know if they're completely discontinued them or not. But that just gives you a rough view of it. Let's see, this was at the back again for the Fulton County Airport. It looks like it's probably missing a part of the element. It's just a vertical dipole, where mostly they have the antennas, the corner reflectors. That's it. And here's a better picture of one. It shows the corner reflector. This one also has the NDB at it. Okay, that's not very interesting to know. So let's move on up to localizer. Now we're actually getting in the VHF range, and it's part of the ILS system. It operates on 108 to about 112 megahertz on odd tenths. And as a reference, your FM broadcast band ends at 108 megahertz. So this is just above that. Transmits power of 100 watts, and it marks the center line of the runway. And if you've noticed on this road, if you go out, Hosea, you go out it, you'll see it on the left at the end of the runway. And it marks, like I said, the center, and it transmits two signals. It transmits modulated at 90 hertz and at 150 hertz. And the amplitude of the signal that the aircraft receives determines if he's centered. If they're both the same, he's in the center of the runway. If he's left or right, the other one will show up. And you can actually, if you tune to, if you're mobile rig or tune aircraft, tune it to 109.95, And as you drive across it, if your speaker reproduces 90 hertz, 150 hertz, you can actually hear it change as you drive by the end of the room. I've done that. All right, this is one of the instruments in the aircraft, and this vertical line here determines your position on the runway. And if you're too far right, this line will move to the left. That means fly toward that line and get it back centered. Same way this way. There's also glide slope, which I'll cover in a few minutes. And this is how high it's a glide path into the runway. And if you're too low, this will be up here, and you need to fly up. And if it's too low, you're too high, you need to fly down. So that's basically how it works in the aircraft. This is a little diagram showing you. Here's the runway. There's the antennas, and transmit the 90 on this side and 150 hertz on this side. Here's an actual picture of the one out here in the runway. And they're Yagis. Yagis pointed down the runway. I looked for a view from the top, but you couldn't see much. This is actually a street view from Google. And, go back to here. This is what shows you the left and right side and it gives you the localizer frequency, and it actually transmits a ID again. India Tango X-ray Papa. So the pilot can listen to it to make sure he's on the right frequency. Okay, I think that covers the localizer. So let's go on up in frequency. VORs are next. And they operate on two ranges, the 108 to 112, 50 spacing on even tenths. And that's called a terminal VOR. And the range is short on those. The others are high power, 112 to up to 118 megahertz. And they're in 50 kc steps. And you have different classes. You have a terminal VOR, which is good about 25 nautical miles. You have a low altitude, which is 40 nautical miles. And high altitude range is 100 miles. It's interesting how they work. They transmit a beam, it's electron being rotated, 30 revolutions per second. Now, if you imagine this, let's say you took a Yagi, three-element Yagi, and you turned it vertical, and you stuck it on a motor. You turn the motor on, and it starts spinning at 30 revolutions per second. Of course, your coax is going to wind up. Don't worry about that. That's what it's doing. It's turning that fast, but it's done electronically through about 60 antennas. And I got pictures of those. And it's modulated with an AM frequency of 30 hertz. And the phase of that signal is delayed by the direction that the antenna is turning. So if it's pointed north, it would be 0 phase. If it goes around, if it's pointed 180 degrees, it would be 180 degrees phase difference. And then it has an omnidirectional reference antenna, which transmits in all directions, and it transmits at the same frequency, but they modulate 30 kilohertz on a FM subcarrier on there. And so then in the aircraft, it compares the AM signal it receives and the FM 30 hertz to get a phase angle. And then that's the radio from that station. He looks at it and says, okay, this station is in that direction. And I'll show you a picture of it. And if it's, the indicator will tell you you're to or from that station. It also broadcasts the AM ID in Morse code. Accuracy is plus or minus 1.4 degrees. And this is a picture of what the instrument would look like. In other words, this line can move left and right. So if you're flying toward, it says from. So you're flying from the station, and this is the direction. If you're flying to, the to will be left. And so that's how it's like a non-directional beacon It's more accurate, and you don't run into the night time problems of skip on the low frequencies. This is a picture of one, and you notice that it's like they got a ground plane under it. Here are the 60 antennas all the way around it. Here's the reference antenna in the center, and you've seen this before. This is a DME antenna. You saw it in that first few slides. So this station provides the VOR plus DME, and we'll cover DME later, but it's higher frequency. Here's a difference. This is called a Vortex. It's a VOR. You see the normal antennas. You see here the directional, the non-directional antenna center, and then what's up on here is the TACAN. I'll cover TACAN in a few minutes. That's used by the military. Also, your DME is located inside of there, so this provides distance, slant distance. Here's the Atlanta airport. Again, Google Earth. You can see the antennas going around it, and the Omni antennas in the center. And it says Vortex, so that means it should have a TACAN. Where's the antenna? Well, you go down here, it's down here, off to the side. And I had a hard time figuring out why I couldn't see it. And I expanded my view and found it. Here's a aeronautical chart for the Atlanta airport. It shows the Vortex frequency channel. Now, the channels are used by military aircraft rather than, I guess they can't count frequencies, so they just got thumb switches and channel numbers. So they don't have to worry about megahertz, kilohertz, whatever. And the call sign is ATL, and there's the Morse code for it. Let me mention something here that might be of interest. All runways have numbers. You may have seen that. Have you ever wondered how they're numbered? Well, this is a good example. You've got 2 parallel runways on the north side, 2 parallel runways on the south side, and you have another parallel runway that's offset. And so what they do on numbering them, they take the azimuth. So if you were looking here and looking this direction, you'd see it would read 90 degrees. And they drop these always a 0. So this is runway, this is runway 9, and it's left and right. So that's how they number those. If you're coming in from the east side, they would be numbered 27, left and right. Well, you can't use the same number again on this side, so they decide to use 8 left and 8 right, and 26 left, 26 right. And this is separate, so this is 10, just runway 10 and runway 28. But I just wanted to mention that because you'll see talking about runway numbers, and that's where that comes from. Example right here, you stand at the end of the runway and you look down, it reads 249 degrees. Well, they round it up to the next 10, so that makes it 250, then they drop a 0, so that's runway 25 and runway 7. The other end's always 180 degrees in the other direction. Let's see, localizer, okay, ACARS. This is a system that's fairly new, it's 78, but I think it's really in use now. The aircraft transmits a data stream on one of these frequencies. They transmit the information to the ATC or the controller, and they also transmit the information to their company, like Delta. It gives them the out-of-date time, off-ground time, on-ground time, in-gate events, flight plans, weather, equipment health, status of connected flights, and all that. You can actually receive this if you have a receiver in the VHF range, and there are apps that you can download to PCs that you can actually decode it. I haven't tried that, but they say that's easy enough to do. Okay, glide slope. I mentioned that earlier. It's part of the instrument landing system. Operates on 329 to 335 megahertz, power 5 watts, and it's paired with the localizer frequency. So the pilot doesn't have to remember all these frequencies. All he has to remember is the localizer. The glide slope is automatically tuned for him. So that makes it fairly easy. It's identified by a 1350 hertz tone, RSID. The beam angle is at 30 degrees elevation. And there's two transmitters, just like it was with the localizer. This again is the vertical 90 hertz tone and 150 hertz tone. And if it shows if they're equal, then they're on the center of the glide slope. And the new systems use what they call end-fire antennas, which I'll show you in a minute. Here is the example. Here's the runway. Here's the antenna, and they're showing the old style antenna. But as long as the airplane is right in the center, he hears both the same, and then his indicator will show that. Here's the old style antenna, which looks like three corner reflectors. And there's a picture here is a Winder Airport. Again, pink color, but there's the antenna there. Show up at all? That's the biggest I can get it. And then the new style is called in-fire antenna, and that's what they have here at this airport. And this is just a picture, not here, just someplace. They look like that. Here's the one here for this airport. This is the Google Earth view. Here's the runway. This is the southeast side, and so you'd be landing in this direction, and you have three antennas. And I'll show you what there is. This slide here. They call this the rear antenna. They call the center the clearance antenna, and then the front antenna. I haven't studied how it works. The reason they're using this is because ground effects, water effects don't affect it. Whereas the Yagis, or the corner reflectors, they have problems keeping them lined, according to my sources. And anyway, that's pretty much covers glide slope. By the way, if you go on the website, you don't have to go, all these are linked to the next page. You can go directly there. But I'll go back and, so PayPause. It was decommissioned in 2000. I think all the equipment's still there, operational. But anyway, it's precise acquisition, vehicle entry phased array warning system. It's to detect missiles being launched. And it operated in the amateur band, 420 to 450 megahertz. And there used to be a rule, the FCC, if you were in 100 miles of one of their stations, you couldn't get on, couldn't have a UHF repeater. The nearest is Warner Robins. So I'm sure it affected this area. Now, I don't think it's any, they're not operational, so I don't think it's any issue. But that's where we should, and we're secondary in that band. They're primary. Peak power of 580 kilowatts, and range is greater than 3,000 miles. Consists of two-phased antenna elements. I'll show you a picture. I won't go through all this. There's a lot of stuff there. There's actually 4 sites. There's one in Cape Cod. There's one out on the West Coast. There's one in Texas, and here's the one in Warner Robins. And if you notice, this is the phased array right here, same way as over here. And this is still there. And I'm assuming they can turn it on if they want to. I don't know. I couldn't find much about it. It just said it's off the air. But it is in our UHF band. DME. This is the distance measurement equipment that I showed earlier. Operates on 960 to 1200 megahertz. Aircraft transmits in that 1023 to 1153. The ground station 960 to 1215. The DME frequency is paired with the DOR. Again, you don't have to know that this is on 900 and something megs. It's automatically tuned for you. Ground station output power of 1 kilowatt peak. Aircraft transmits 2 3.5 microsecond pulses at a rate of 150 pairs per second. When the ground receives it, they add 53 microseconds and then retransmits the pulses. And the slant distance is determined by the round trip time. So that's how the aircraft gets the distance from that station. And the ground station is identified with a 3-letter Morse code if the receiver is tuned to it. Here's an example of what a display in a cockpit would look like, and it's showing you 2 navigator receivers tuned to different VORs, and it shows the models, each one. Here again is the antenna, this pole that we saw earlier, and I think that covers it for DME. DME, ACSB, okay. Automatic dependent surveillance broadcast. This is again broadcast by the aircraft, and if you have a receiver like a SDR play or some receiver that will receive these frequencies, there is an app that you can load on your PC that you can feed the sound into it. I've actually done this, and it said Delta flight so and so altitude, speed, and everything. All that's broadcast, and all you have to do is decode it. Okay, TACAN, this is the tactical navigation system. It's for the military. It gives the slant range. It's actually using DME equipment for that. And it also gives a bearing. It's used on the ground or ship station. It's more accurate than a VOR system. And the VOR is combined with a TACAN. It's called a Vortex, which I showed you earlier. Operates in the 960, 1250 megahertz band. It's identified with a Morse ID again, and 1350 hertz tone. Accuracy plus or minus 1 degree azimuth and 0.1 nautical mile distance. And all your carriers, ship carriers, will have this because that's how the fighters learn how to get back to the ship. And transmitter range 200 nautical miles with a 400 watt transmitter. Okay, secondary radar. I actually worked on this in the Air Force. You have a ground interrogator that operates on 1030 megahertz, and the aircraft transponder operates on 1090. And basically, if you're flying a IFR instrument and you file a flight plan, they will assign you what they call a squawk. This is a 4-digit octal code. Only you will have that code, so they can identify you. And when the ground station interrogates it, mode A, it will return with that code, and their computers look the code up and say, okay, that's Delta 123 or whatever. If they have mode C also replies with the altitude, so they can get the altitude of the aircraft. The ground directional and omni antennas are mounted on top of the primary radar, and it provides aircraft identification, and they have a function what they call ident. The controller can say, hey, Delta 123 ident, pushes a button, and that'll cause the CRT screen to bloom, and so he can, oh, that's you, because he's going to see a lot of aircraft. It was originally developed for military, for IFF, identification friend or foe, and that's when you have actually dogfights and you have controllers, well, who's the good guy? And that's what that was developed for. This is a picture of a primary radar with a secondary antenna on top of it. You don't see the omni antenna, and I'll explain that in a minute. This is what the controller sees. A primary target with no secondary radar would just be a mark like that. But this would have a mark and a second mark. This is a mode C, and then this is American Airlines. I guess that's a 076, 15,100 feet. It's mode C altitude, and the ground speed is 230 knots. That's calculated by the computer because when a radar paints an aircraft, he's going to hit him several times because of the pulse rate. And so he can calculate, he moved 2 feet, he moved 3 feet in that time, so he can calculate his ground speed. It says he's also equipped with TCAS, which I'll talk about in a minute. And back to TCAS and FAA radar. And this is the primary radar. You have two types. You have what they call the air route surveillance radar, which is long range. operates in the L band, and the ham band is inside of that, 23 centimeters. I'll talk about that in a minute. The ASR, Airport Surveillance Radar, is 60-mile range and operates in the S band. And at the airports, you'll probably see that one spinning, unless they put it in the radome. You'll probably see that one. Most of the primaries are all in the radome. The primary, or the air surveillance radar for Atlanta, is located off of Windy Hill. If you're on 41 and you turn on Windy Hill and go west, about a mile on the left, you'll see a radome on the left, and that's where it's located. When I worked over near there, on my desk, I had an R7000 receiver, which is a ICOM VHF receiver, and I could tune in the radar. And it was on 1290, which is in the ham band. And it wasn't any problem knowing what it was because I worked on it. But I don't know if it's there now. I can't hear it out here, it's too far away. But if you're driving over that area and you have a receiver that tunes that frequency, that's what you'll hear. You can actually hear the 1030 frequency too, but it's not as strong. Yes?
What does that sound like, radar?
It's a buzz. That's the best I can say.
Yeah.
It's a buzz. Because you're actually hearing the, pulse, and you actually hear it sweep. In other words, it's strong, and then if you're close enough, you hear the slight lobes come around. And then when you're in the beam, it'll be loud again. 12 seconds for it to go around. Here is, and I won't go through this again. This is in the online. It shows you the range again of the two types of radar: the power, the pulse repetition rate, antenna size, and the revolution of the antenna. This is the primary again. This shows the secondary antenna on top with the Omni. Now the purpose of the Omni is as the aircraft gets close to the radar, the side lobes will start picking up the replies, and the scope will have a circle on it. So, I mean, the controller can't see what's going on. So when the signal that the Omni picks up is a certain strength, it disables that aircraft as far as it's being displayed. So that's the purpose of the Omni antenna. These are all normally inside a radome, so I don't know of any that's it's not. The ones I worked on were inside a radome. This is the one you may see at the airport. This is the ASR spinning pretty fast, and that's what it looks like. I think up north they're all in radomes themselves due to the weather. And that's, okay, let's go on back to the next one. Radar. Okay, GPS, which you all probably got one in your hand or in your pocket. It's a all-weather, three-dimensional navigation system, developed by the Department of Defense and maintained by the U.S. Air Force. It uses a constellation of 32 satellites, 31 in use and 1 spare. And they're located in 6 orbital planes. They have a 12,600 mile circular orbit with a 12-hour period. And it uses time difference to determine position. Back to your curves I showed you earlier. They broadcast CDMA. Now, that's the type of radio, get the term, but right, that's what it means, but there's a term for all of them. CDMA is code division multiple access. You have
spectrum.
It is spread spectrum. You have TDMA, which is time division multiple access, and you have FDMA, which is frequency division multiple access. There's probably a whole program on those and how they work. But basically, the FDMA is what you're all used to. You change the frequency to listen to something. TDMA is fairly easy to understand because it's dividing everybody up into time sequence. You can talk, you can talk, you can talk, you can talk fast enough where you don't tell the difference. CDMA is magic. I don't know of a good analogy of how it works. So that's all I'll tell about that. Okay, you've got a course acquisition accessible by the general public, and then you have a precise code which is encrypted for military use. The satellites transmit a time, and if you have a GPS receiver, your clock is accurate because he gets it off the GPS. satellite. It also sends the satellite position and the health of the satellite. And it takes 3 satellites to get a latitude and longitude. 4 satellites required for an altitude. Usually 8 satellites are in view, and the planned accuracy is 33 to 66 feet. And you get within 1 feet if you use L5. And you see, that I show frequencies. Yeah, I showed L1 is 1575, L2 is 1227, L5 is 1176, and it was supposed to have been turned up last year. With that, you'll get 1 foot accuracy. Now, your phones don't have that receiver, so you won't get it first. It'd probably be expensive to get the 1 foot accuracy, but that's what they say. The planned vertical accuracy was 66 to 99 feet. And this is a cute little, is that showing up?
Yeah.
I got this, it's showing the place on in the United States, and as it rotates, it shows the satellites, and it shows the switching between the satellites. That's kind of an interesting diagram. Okay, back to Raycon. Okay, it's a marine.
Question.
Yes.
GLONASS, you have any comments on that?
No, I mean, I know about it.
Most of the latest things use both, so.
Okay. GLONASS is the Russian GPS system. Am I right on that? I think.
Yes.
I haven't studied. I just.
There's a European version coming out.
Yes.
so-
Right.
Really?
Yep. Another one. So I guess if we lose GPS, we can switch over. All right. Marine radar beacons, our Raycon. And they're operated by the Coast Guard, and they mark lighthouses, navigational buoys, bridges, offshore platforms. And when triggered by the ship's radar, they respond with a line of dots and dashes forming a Morse code character. Operates in the 2900 to 3100 megahertz S-band or the 9300 to 9500 X-band, marine radar band. And you'll see here a example, but before I go there, you can go to what they call the U.S. Coast Guard Light List. It lists all the lighthouses, buoys, anything that is active that the Coast Guard maintains. And I picked this one, Flowery Rocks Lighthouse. It gives the position, characteristics, the flashing white light, 10 seconds, and it has 2 red sectors. Height is 110 feet, and the range white is 15 miles, and the reds are 10 miles. And this is the description of it in daytime if you were looking for it. But what I wanted to show you is the remarks, Raycon O, and this dot, dot, dot. So, also, if you go to the marine charts, it shows it, the lighthouse, and the range, 7 miles. That's the indicator. Here's the O. It tells the navigator that it's going to return that. Now, the one I want to show you, I couldn't find, so it must be not operational anymore. This was up in Boston Harbor, and it sends a cue. You can't see the space there because of the range mark, but da 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 da. And in other words, it's pointing to where the ship evidently is down here, so it points direction. Because the radar hits it and it transmits that back. So that's kind of a neat system. They're still in operation. Let's see. Okay, the last item is wide area augmentation. WAS. I'll leave it at that. It's similar to the differential GPS. It enables aircraft to rely on GPS for all phases of the flight. It measures the difference between a known fix and what the GPS is reporting. And the difference information is uplinked to 3 commercial satellites. That's those. Accuracy is better than 3 feet laterally and better than 5 feet vertically. So that gives you now with the new L5 with 1 foot, I don't know how much this will be used, but it's there today. And I wanted to show you these charts. This is just a chart of the frequencies. And starting down here with Omega, DECA, Loran C, the NDBs, the DGPS, and oh yeah, we got a band down here at 2,200 meters. How many's on that frequency? Nobody? Okay. It's down there. We also have a 630 meter band. And I've actually copied Morse code IDs at night. So there's somebody sending out some information. All right, moving on up, this is the top NDB, which is 500. Now we broadcast. There's CNN, WSB, just to give you a reference. Move to the next one. This is the top end of the broadcast. Shows you where Loran A was. And again, this is a 160 meter band. Move on down, we jump up into megahertz. And this is the localizers. Show you the frequency, and these are actual localizers. Atlanta 27 left, Atlanta 9 right, Fulton County 8, Atlanta 8 left, LZU 25, which is down the way here, PDK 21 left, and then Atlanta MGE is the Dobbins Air Force Base, and Winder and Fulton County 31. And then up on the top side, you have your VORs. And Rome, VOR is here, LaGrange is here, PDK is there, and Atlanta, Vortex is there. And so move on to the next one. This is showing the glide slope frequencies. So again, on UHF, and it shows you where they're located, the different airport runways. I won't read those to you. PayPause, it shows that it covered the whole 70 centimeter ham band. And as we're going up in frequency, we get into the DME, the frequencies, Athens, Paris, Vortex. This is the secondary surveillance radar interrogating frequency, and TCAS is there. Savannah, Vortex, Vortex. Secondary radar receive, and DOB, again, Dobbins or MGE, they use both of them. TACAM, they actually have TACAM at station there. ODF is Foothills, VOR, that's north of here. Macon, Vortex, Rome, LaGrange, DDK, and Atlanta Vortex. Then the last one is showing you the GPS. L5 is located there, and Marietta, right here, is their primary radar, or it was, about 5 years ago. And it operates in this band, and that it was located there at that time, right in the middle, well, not in the middle, it was at 7 centimeters, 23 centimeters goes from 1030, 1240, okay, 1240 up to 1300. And the air surveillance well, the primary radar covers the band 1250 to 1350. GPS L2 is there. All right, back to the references. This is a link to the FAA Airman's Information Manual. It covers everything about aviation, but it also covers the parts that I've gone over. Google Maps, which I'm sure you're familiar with. Wikipedia web pages, tells you a lot of this info comes, especially the systems that have been decommissioned, because there's not much on the regular sites. If you want to know about aeronautical, like nav aids, you can click on this, and we can go to LVU. Oh, did I type? It changed it on me. Got a page? Yeah. LVU. Well, my computer changed it. Try and spell it. LVU. See, it wants to change it to LOU. I'll cancel that. See if it finds it. Nope. All right, we'll do it another way. We'll go to the airports and we'll put in LZU there. Okay, Gwinnett County Airport, and it tells you all about it, everything you want to know about this airport. I'm not going to go through it, but that's where you can get that. Another thing that may be of interest is the aeronautical charts, which I showed you. This will take you to the aeronautical chart page, and this is showing you the airport here. Shows you information about it, runways. These are obstacles. For example, it says at this location there's a 260-foot tower, I'm assuming, and it's above sea level is 1,236 feet. Just to show you that. But all that's online. And anyway, this is a link which will be on the website, GAR's website, to this presentation. And so that's it. Any questions? Go ahead.
You mentioned SIF-IFF. Is Beaumark still in existence?
I do not know. I do not know the answer. Go ahead.
Other than, last year I did a kind of local expedition to a place in North Carolina, and I noticed a few miles away there's an FAA radar site right along the coast. Are there any restrictions operating amateur radio when you have a site like that?
No. Again, if it's a long-range radar, then they're on the frequencies that the UHF 23-centimeter band, and only restrictions if you were operating there and then where it messed up the radar, then remember they're primary. So you would have to.
For HF, there's no problem.
No problem there. I wanted to mention one other thing that's kind of neat. You may know about this, but this is gonna back on the internet. On Google Maps, you got the satellite. You click that. And I wanted to show you this about Street View, which you may or may not know. This is actually my QTH, which is right here. But if you turn on Street View, which is this little man down here, you'll see blue lines. Any place there's blue lines, that's where that Google car has driven, taking photographs. So you can click on the line, and my house, well, it was taken before my house was built. That's all there. So what do you do about that? Well,
You're in the woods there?
you get an app for your phone. You get an app for your phone. It's called Google Street View. And what you do with it is, go back, close this, and you look for these little circles. Come on, circle. Any other time, I would show you the circles. I don't know why. It's there. No, it's a blue circle, like this, but that's not it. Oh, yeah, I turned it off. I mean, the man turned it off. Okay. All right, here's one here. See this little circle? That is what I took with that app. So now, if you click on it, and you go to Street View, again, we're slow internet download. My house is here, and it's a 360 view, and I took it with my phone. And as you turn the phone, there'll be a circle and a dot. And as you move, you want to get that dot in that circle, and it automatically takes a picture. You'll hear it click, and you move a little more, all the way around. You go up and down, and when you're done, this is what you end up with. A complete 360 of, and you can actually zoom in on them. Now, you can publish it or not publish it. This is published, so it's anybody in the world can get to it. But you have the option of not publishing it. Also, on the app, if you have to take a picture of a person you don't want your picture, or a license plate, there's a blur option. You actually put it on and touch it, and on the app, and it blurs there. their face. But what I really like about it is if you're going somewhere on a trip and you say, well, I've never been there, I wonder what it's like. Well, to give you an example, go to Biltmore. If you go there and you zoom in, and you turn this back on again. Now, yeah, got to download it. The actual the Google car drove around here. Haven't come up yet. But so there is a blue line all the way around this. But all in here are these little circles. And that's where people have been there and actually taken their own picture. And so if you're going someplace and you say, wonder what it's like, well, odds are, there they are, they popped up. So you can see the blue line all the way around it, but if I just pick one of these, you click on it, and then this is where somebody has used the app. Do it right.
Is there a way to tell what date that picture, the picture is from?
I think so.
It does say May 2018 in the upper left corner. I don't know if that's the picture or not.
Well, I can't.
Sometimes you wonder how old it is.
Well,
You gotta turn it back on, you blue dots one.
This is all part of Google Maps?
Google Maps.
Being Google is stripping all the metadata from the
The point, what you need to do is download the app. It's Google Street View.
Yeah, and this one says July.
And as soon as it comes into focus, use it, shows you the picture. So, see, somebody did this. Has nothing to do with navigation, but I use this all the time. It is great, especially if you're going someplace and maybe somebody's already been there and you say, oh, well, that's what it looks like.
Well, you say go right by the two guys. That's right.
So anyway, that shows you the full thing. All right, enough of that. And all of that.
We get 360.
Yeah. Back to there, and that's it.
Right there, John. Right there. Right there. That's good.
Is it on still? Well, we're here, Jerry. We'd like to at least give you this certificate. Appreciation for your great program tonight. Learned a lot. Thank you very much.